Welcome to the Digital Additive Manufacturing Marathon Conference. I'd now like to invite Sherri McCleary, Director of Business Development of Additive Manufacturing at Kennametal, to the stage. She will speak about printing the future of hard material solutions. So a little bit about her. She is responsible for driving business growth and leveraging additive manufacturing technologies to deliver high-performance components using Kennametal's hard metallic materials in wear and other demanding applications. Prior to joining Kennametal, Sherri spent over 30 years with Alcoa, then Arconic, working in all levels of technology development and leadership. She has a strong passion for mentoring others, developing strategies, connecting people and technology to deliver impactful value, and giving back through involvement with nonprofits. Thank you, Sherri. Looking forward to your presentation.
The groups, business groups within the company, our industrial metal cutting tools, and our infrastructure businesses that include some of our wear solutions that I will be talking about today. And we serve a lot of major markets, including earthworks, energy, general engineering, aerospace, and transportation, among others. So for starters, what do I mean by components and solutions that fall into what we call the wear category? These are products and materials that are in environments that are very tough conditions. They're materials that are very hard and resistant to erosion, corrosion, wear, high temperatures. Some of the typical applications include mining and earth cutting, oil and gas, power generation, construction, industrial tooling, as well as in a lot of process industries, including processing of materials, food, and chemicals, anywhere where you may have aggressive, corrosive, or abrasive gases, liquids, or solids passing through a system. So why additive manufacturing? All of the typical reasons that everyone's very familiar with as it relates to design optimization apply to wear components as well. We're often dealing with complex geometries, the need for customization, parts consolidation. Also enables the use of some materials where you can create different metallurgical properties, weight savings, and improved performance. But one of the big issues that additive addresses in wear components, by very nature of the fact that they do wear, they are often replacement parts. The frequency of replacement is unpredictable at times, depending on what's passing through a given system. So supply chain benefits of additive are one of the key drivers for wear components. The ability to shorten development cycles, streamline and compress the supply chain, and rapidly deliver parts in an environment can be very important. Downtime can be extremely costly. So things like printing on demand, digital inventory management, reducing shipping and warehousing, and carrying of physical inventory are very important to this market segment. So where are we focusing to deliver into these demanding markets? We have started with two material families for Kennametal. To the from some of the first uses and development of tungsten carbide in the U.S. And also we are the developers and owners of the trademark for the stellite materials, which are cobalt chrome. So these materials kind of function in this space where corrosion, erosion, and high temperature overlap. And if you look at this kind of material map of just a couple of key performance attributes for these types of materials, toughness on the x-axis, hardness on the y, you can see where tungsten carbide falls in the green, in the blue. There are several grades of tungsten carbide, several alloys in the stellite family, and they're getting up there in the range of, in some cases, what you would get with ceramics. And so we're talking about very hard, very tough materials. The stellite is a cobalt chrome based material, and the tungsten carbide is basically a non-matrix composite where you have your tungsten dispersed in a matrix of cobalt or cobalt in combination with other metallic materials in the matrix. So when we look at to complete the solutions for wear components, it's not unlike what you have in a lot of other segments, whether metal or plastics or otherwise. But in this case, we're managing the metal powder characterization and customizing that for additive to make it both more printable and to get the desired properties in the end. We are doing prototyping and optimization of the design for manufacturing. And then we are printing production components for the wear markets and also focusing on post-print processing and finishing that would include your, in this case, sintering or hipping, as well as finished machine grinding. So what we bring specifically, we produce our own AM powders. As I said, we have a long expertise in tungsten carbide, cobalt, as well as nickels. We are producing powders that are sold to others who are printing, but we're also customizing powders for the components that we're producing. We work with customers on collaborative design to make sure that the component is designed for printing and post-print processing, prototyping of fully functional parts, and then we are moving to serial production using binder jet and laser powder bed systems for development of our powders. We do hold some foundational IP on the printing of tungsten carbide and the development of our stellite alloys. That gives us some differentiation and puts us in a unique position. With regard to post-print processing, this is very critical, as most are doing metal printing realize. They come out the finished part ready to go. It typically requires some level of heat treating. In the case of our hard materials and of machining or grinding to get both your final engineered properties or metallurgical properties as well as the geometries and dimensions are required for the final part. So for our hard materials, for the as well as some of the stellites that we're currently printing, we are primarily focusing on binder jet technology. And as a brief description, this technology, basically you have your powder reservoir or tank that's distributing that material into your build tank or your build box. In your build box, layer by layer, you're putting down a very thin layer of your liquid binder on the powder to create your bound layer of your powder, where you're basically your binder is gluing that powder together layer by layer, and what you end up with is a green part that then has to go through debinding, burning off of that binder and cinch it to your final metallurgical properties. In the sintering operation, you do, as you go up in heat, get consolidation and densification of your component. Achieve 98 to close to 100% density just following liquid phase sintering, and then we can get to a full 100% densification, if not through sintering, by a follow-on hipping operation. Some of the advantages with the binder jet technology is the fact that it's the only reliable technology at this point for printing of very hard materials like tungsten carbide. It also does not require that you build any supports in your print bed. You can use the entire volume of the build box and build all the way out to the edges. There's no heat or shield gas required in the printing operation. You do end up with what's considered a green part, just like other powder metallurgy processes, and your final metallurgical properties then are established in the sintering furnace, which also creates a flow path that's much more aligned with traditional powder metallurgy. So when it comes to qualification, it's more about if you qualify and control the incoming copper characteristics and the final sintering operation, that is where your final properties are and your final geometries to some extent are truly established. So it's much more akin to traditional powder metallurgy. So as we look at how do we manage through this process, there are a lot of key input variables around the powders, the part design, the printing, the curing, the debinding and sintering that all will be responsible for and interdependent to achieve your key output variables from both the ability to print, flow, and sinter all the way through to the final density, grain size, and properties of your part. So it is a complex management and understanding of the science and interdependence between all of these key input variables to make sure that you are managing what you get coming out on the other side. So when we look at what we're achieving, these are two of the materials, Kennametal materials that we have refined, customized for 3D printing in the binder jet technology. They are stellite stick, AMK, which is our additive specific stellite 6. Stellite 6 is a cobalt chrome alloy that has dispersed carbides that makes it a very high wear cobalt alloy. It's one of the most widely used cobalt alloys, particularly in wear applications. It brings a good balance of wear resistance, corrosion resistance, and property retention up to about 500 C. And I show a little spider diagram here. I had to kind of normalize these so I could get the diagram to I'll fit everything on at the different scales. But what it basically shows you is that when we compare what we can get with additive manufacturing to an investment cast stellite 6, we are basically overlaying with the same properties in ultimate tensile and tensile at temperature, elongation, yield, density, hardness. And we actually have this is volume in the additive where we have a little bit less volume loss. They're also very analogous to what you would typically see in a cast structure with stellite 6. With our Kennametal tungsten carbides, we have AC89. This is a cemented tungsten carbide that has a 17% cobalt matrix. Again, a good balance of wear and hardness that you would expect for tungsten carbide, but with the 17% matrix, it's a tougher material. And again, it directly overlays with what we see with respect to the three primary properties that are always measured, which are transverse rupture strength, density, and hardness. Additive directly overlays with the traditional pressed and sintered powder metallurgy. We have a relatively coarse grain, but a very nice grain structure that we can achieve through printing and follow-up sintering. We also are introducing additional alloys in the stellite family, as well as different grades in the tungsten carbide family. These two are already approved for production parts. We are producing production level parts with these two materials. And in addition, on the tungsten carbide side, we are prototyping with products that have a lower matrix content, so cobalt matrix down to 12% and 10%. And we are also introducing a carbide that has a matrix that's a combination of cobalt and nickel that will be a more corrosion resistant version of the tungsten carbide grade. So when we look at what we can achieve as far as geometries, this is really just a small sample of the many parts that we have been producing that range everywhere from some very small components that you see in the lower left-hand corner that are relatively simple to some very large and complex parts that you see in the upper right-hand corner, including one of our largest, this concept for a drill head that's solid at our 17%. This part is roughly the size of a soccer ball. It weighs about 50 to 60 pounds or 23 to 27 kilograms, so a large, heavy part. And this is one of our larger stellite parts. This is a flow control stack that measures about 12 inches tall. And if you look, this is a cross section of it. While it doesn't look particularly interesting on the outside, one of the things that we are leveraging with additive a lot with wear components is the ability to do very complex internal flow channels. And you can see that with the cross section here taken from this part. And you can see the flow channels in a section of this part as well. So in a lot of cases, as you can imagine, in process industries, you're flowing materials, products through these systems where you may be trying to control the pressure, the flow of a liquid or gas, or you may be just running it through your process operations and you need wear resistance. And additive is allowing some very unique concepts around how to manage flow control in some of these components. So we can do everything from some fairly large simple parts to some, or fairly large complex parts to some fairly small simple parts. And I don't know if you can see me on the screen because I can't see myself on the screen. But this is an example of a relatively small part, but fairly complex, where we are actually printing functional male and female threads. And these are just as sintered with no follow-up machining or grinding. This is in tungsten carbide. So this is a great little part to show the ability to really manage those tolerances and geometries through printing and post-sintering. While most of the components still require some follow-on machining and finishing, we often talk with our customers about one of the things with additive is really start to think about how many of your surfaces are toleranced based on the fact that they're subtractively manufactured, and every surface is, by nature of the manufacturing flow path, machined, versus how many of your surfaces truly require a tolerance to fit up or dimension. And if you can see this part, which it may be a little difficult to see on camera, but around the center here, this was a region of the component where tolerances were not critical, and that you can see that's a little rougher. That's the as printed surface, versus fit up and threading on either side of that did require final machining. And again, the interior is not machined, it's as printed. So again, post machining is typically required for some of these complex shapes, but you really need to stop and think about what surfaces are really critical and require that kind of dimensional control versus which surfaces can you live with as printed, because it can take a lot of cost and time out of the operation. So one of the other advantages, and I believe that the EOS guys talked about this a little bit, is the ability to kind of pack your bed with. Not only could you have, we're running parts where we have small ones that we're packing the whole bed with 1,000 parts, and that are all the same, and we have applications like that, or we are packing your bed with same materials but multiple different parts. You see this photo in the middle is a photograph of 4 large components that are all different using the same tungsten carbide material. These are just coming out of the powder bed. And the photographs you see are images during the print operation of a layer in the bed. And so you can see the ability to print multiple different parts with very different geometries. So this really allows us to start to think in terms of how do you not only take advantage of the fact that you don't need dedicated tooling with additive, in this case we don't need to build supports, but we also have to figure out how can we maximize efficiency through, with each build that you run, packing your bed with as many parts, not necessarily the same SKU number. It could be multiple SKU numbers, multiple customers. The real advantages of additive is to figure out how you use that ability most efficiently. So we also find the opportunity to really optimize with our customers, not only the ability to do production-ready wear components and deliver the same performance that they're accustomed to in traditional flow paths, but to really serve our customers with new business models. So guys, we think about what does additive bring? Yes, it brings the ability to do complex shapes. Yes, it brings the ability to create some really differentiated materials and designs, but the ability to serve our customers with things like digital inventory, improving uptime, reducing cycle times for development, being able to reiterate and try things quickly, get components in the field and trialed quickly is proving to be one of the greatest value propositions of additive when we talk about wear components. So that concludes my slides. I'm open for any questions. You can visit us on our website and also join me at table 6 on floor 4.
Perfect. Thank you so much, Sherri, for being a great sport on this. We're going to allocate 3 extra minutes for Q&A. So one of the highest demanding questions created by James Howell is, what's the business case for the method given the additional preparation processes and therefore costs and having to produce your own initial materials?
I guess I don't completely understand the question. Is the question the costs associated with producing our own materials specifically? Because we were already producers and suppliers of powder metal today into traditional flow paths. We produce tungsten carbides that go into all of the products that we produce today. We own the internal supply chain for that. And our Stellite brand of materials, we produce through gas atomization, cobalt, nickel, and iron-based powders that we sell into additive as well as other traditional manufacturing. So these were capabilities we had, and we are leveraging both our material science expertise and the production capability to produce optimized powders for both our parts and for some of our customers who are printing on their own.
Perfect. And then a question from Pete Ferguson. Do you outsource the post-processing portion? Investment cost for the equipment is likely high relative to its capacity usage.
So we do outsource some of the post-processing. We do what we can in-house, depending on timing and capability. And yes, the post-print process capabilities are costly. We do have all of our own sintering and hipping capability. That's something we hold as kind of a key competency. So again, those were investments we already had as a result of that being standard steps in traditional powder metal processes. And also with respect to post-print machining and grinding, we have capabilities in-house as well as we will outsource. But yes, when you start to look at getting into 3D printing, you really have to look at those downstream processes because that can be where the big capital investment and expertise investment may lie.
Thank you. Thank you for that. That's very true. And Thomas Chudy from Extrude Home is asking, assuming the surface finishing of tungsten carbide is challenging, how does it impact the final cost per part when it comes to complex geometries? Which technologies do you currently use? So
yes, any of these materials by their nature, the reason they're wear resistant is they're hard. The fact that they're hard makes them very difficult to machine and grind. So it is costly operations to do final machining and grinding. We are using traditional CNC processing as well as we have used at Extrude Home, and we have used some chemical-based processes for final geometry and surface finishing as well. So there are several options, and it really comes down to with everything, the technical requirements, the cost, and the timing.
Perfect. That's all we're going to have for Q&A. Sherri, I'm going to be sharing with you all the questions that the delegates have. You are quite popular with over 10 questions here. And everyone, if you guys want to connect with Sherri, please do find her at floor 4, table 6 during the virtual networking session. Thank you so much, Sherri, for your time. We really appreciate it.
Thank you. Sorry for the difficulties.
All good, all good. Thank you.